So let's just run through some key terminologies, definition of terms that are, somewhat intuitive for many, and some are experts in it, and some are going to learn something new. You hear terms like artificial intelligence and machine learning, and often it's written as AI ML as if it's one word. And then this paper is focusing on deep learning as something quite different. What is the difference then? Briefly, artificial intelligence is the capacity of an algorithm to assimilate information to perform tasks that are characteristics of human intelligence, such as recognizing objects and sounds, contextualizing language, learning from the environment, and problem solving. So this is probably what you have already learned, because now you know that AI is being used for providing autocorrect, and ChatGPT is used now for writing essays and finding new information, for writing songs, making images, science fiction, and so on and so forth. Machine learning, on the other hand, is a field of statistical research for training computational algorithms that split, sort, and transform a set of data to maximize the ability to classify, predict, cluster, or discover patterns in a target data set. So you can think of AI as the framework within which machine learning is a way forward in actually doing the work, right? So artificial intelligence is owning a bigger umbrella under which machine learning falls, and then deep learning refers to machine learning algorithms that construct hierarchical architectures of increasing sophistication. I speak and sometimes Artificial neural networks with many layers are examples of deep learning algorithms. So we'll see briefly what they mean. You don't have to know the details, because often I myself use AI ML and maybe some deep learning without even knowing that I'm switching from machine learning to deep learning, but we use existing methodologies, implement them for specific problems like downscaling forecasts, global forecasts for Mumbai, to do flood forecasting for Mumbai, and so on and so forth, right? Bayesian inference is a technical term, so I'm not going to read it. Well, maybe let's read one. Bayesian inference is a framework in statistics and machine learning that develops methods for data analysis in which observational evidence is used to update the probability that a hypothesis is true. So it's a statistical hypothesis testing approach. The framework is mostly concerned about treating uncertainty, encoding prior beliefs, and estimating error propagation when dealing with data and models. Does that make sense? Well, if it doesn't, don't worry about it. If you're already an expert, you know that that's a very brief discussion. Causal inference, of course, you know, that's link events, processes, or properties in a system via a cause and effect connection. Convolution, it's much more technical, so I'm not even going to bother to read it. Differentiable programming, it's programming paradigm to generate code that is automatically differentiated such that its parameters can be seamlessly optimized. Don't worry about it. Feed-forward versus recurrent networks, generative adversarial networks, memory effects. So this is important. This is a metaphorical term, meaning that the current behavior of a system cannot be explained without considering the effect of past states or forcing variables. It's the example used here is about CO2 fluxes between the ocean and the atmosphere, or land and the atmosphere. You measure them instantaneously. There are empirical formulas. Typically you measure partial pressure of CO2 in the two media, and you use some wind speed dependence and some coefficients like Schmidt number and so on, and you produce a flux product. But that flux is not so instantaneous. It just doesn't depend on the current PCO2. It depends on various memory things. That's what we mean here. Nowcasting, forecasting, you already know that. To forecast a certain variable means to establish a prediction of its value in the future, days to centuries from now. Nowcasting refers to making that prediction for a very near future. For example, predicting whether it's going to rain in a couple of hours. So nowcasting is a very near real-time information, and this is what we do for floods. 15-minute information will be needed to take decisions on whether to turn on the pump to start dealing with the flooding and so on. Radiative transfer models are very important. These are mathematical models that describe how radiation at different wavelengths, such as visible light, propagate through different media such as the atmosphere or a vegetation canopy. By simulating absorption, emission, transmission and scattering processes, we'll see a bit later that radiative transfer models take the most amount of time typically in a general circulation model or a climate model, and it is very amenable to using AI to reduce the computational cost there. Remote sensing, you know what that is, satellites and other airborne platforms. Could be drones as well, depends on, before we thought remote sensing just means satellite, but as long as you're observing from afar, it's a remotely sensed observation, right? Supervised and unsupervised learning, this is worth reading. In supervised learning, an algorithm learns the input to output relationship after being provided both the inputs and the respective outputs. For example, the input might be a set of photos and the output might be a set of corresponding labels. Then supervised learning takes both of them and comes up with new information or whatever you are expecting it to do on how things are related and so on. In unsupervised learning, the algorithm does not have access to the output, so the goal is to infer the underlying structure of the data itself. For example, the algorithm could automatically separate pictures with different statistical or semantic properties, such as a set of images of cats and dogs. You try to get a intuitive sense for it. Teleconnections is something we all know, that when El Nino happens, things are changed in a distance because the heat source over the West Pacific moves, and that changes Hadley cell, Walker cell, weather, and so far away over northwest US or in southeast Africa and India, things change because El Nino is doing something way out there in the middle of the tropical Pacific. So it is teleconnection, and it's important because that's what we care about. So what are the deep learning opportunities in Earth system science? Then deep learning has achieved notable success in modeling ordered sequence and data with spatial context in the fields of computer vision, speech recognition and control systems, as well as in related scientific fields in physics, chemistry and biology. There's a good example here given in reference 38. Applications to problems in geosciences are in their infancy, but across the key problems: classification, anomaly detection, regression, space and time dependent state prediction, there are promising examples. We'll look at a table in a minute. So that's what this was all about. Two recent studies demonstrate the application of deep learning to problems of extreme weather, for instance hurricane detection, already mentioned as problematic for traditional machine learning to perform. So already you see the difference between machine learning and deep learning. Deep learning actually does go well beyond machine learning. The studies report success in applying deep learning architecture to objectively extract spatial features to define and classify extreme situations, for example storms, atmospheric rivers. If you don't know what that is, don't worry, I've covered it elsewhere, you can look it up. And this is a numerical weather prediction model output that the deep learning will go into. Such an approach enables rapid detection of such events and forecast simulations without using either subjective human annotation or methods that rely on predefined arbitrary thresholds for wind speeds or other variables. So when you define tropical storm and cyclone or hurricane, there are wind speed thresholds, and deep learning can do that without tinkering with the thresholds. In particular, such an approach uses the information in spatial shape of events, such as the typical spiral of hurricanes. Similarly, for classification of urban areas, the automatic extraction of multi-scale features from remote sensing data strongly improved the classification accuracy to almost always greater than 95% in terms of what is really observed and what the interpretation is from the image analysis. Okay, so here is table 1. Conventional approaches and deep learning approaches to geoscientific tasks. I won't read all of them, but we are looking at classification and anomaly detection as analytical and scientific task. And finding extreme weather patterns and land use and land change detection are two examples here of scientific tasks. Conventional approaches would depend on multivariate threshold-based detection, pixel by pixel spectral classification, and so on. The limitations of these approaches are that they can be heuristic and ad hoc criteria in terms of thresholds used for detection, and for land use land change detection, shallow spatial context is used or none in terms of the 3D. So the emergent or potential approaches in these cases, supervised and semi-supervised convolution neural networks, does it make sense? Complicated technical thing, and convolutional neural networks. So we will leave it there. There are similar things about regression, so predicted fluxes from atmospheric conditions, predict vegetation properties from atmospheric condition, predict river runoff in ungauged catchments. There are many papers on these topics, and there are very long list of references in the paper, by the way. You can spend really digging through them and finding some amazing information and details. State prediction, precipitation nowcasting, so short-term predictions, downscaling and bias correcting forecasts. This is what we are doing in Mumbai, where we are downscaling global forecasts to station level to be able to predict floods, seasonal forecasts, and transport modeling. So again, there are conventional approaches with their limitations and what the emergent potential approaches are. Okay, so we'll come back and look at deep learning challenges in Earth system science. So we looked at opportunities, and we looked at some basic terminologies, and we looked at some examples, and we'll come back and look at what the challenges are, so that we can then show a couple of examples beyond what we schematically showed of how data is growing very fast, models are putting out a lot of output, and they have to be matched up in terms of models' abilities to capture details, patterns, etc., so that predictions can be made skillful. And we'll look at how hybrid modeling is envisioned by these authors. Okay, so let's come back and meet in the next podcast.